Okay, good morning everyone, and welcome back to Math 115. So today we're going to talk about sections 2.1 and 2.2. It's a long class, so I am hoping that maybe I can get through both. If I can, then I'll have 2.1 and 2.2 due Friday. That will be when they'll be due. Okay, so that's the homework. So I still have to knock some problems off of 2.1 and 2.2. I'll do that for you soon, and then adjust the due date. Yeah. Okay, so your next quiz is going to be on Tuesday next week. Okay, that'll be on sections 1.6 up until 2.2, which is what we're going to talk about today. Okay, so that's what's going to be on the quiz. So if you want to study for the quiz with me during office hours, your opportunity is going to come on this Thursday. Okay, that will be when I do the quiz review in office hours. I'm also going to have office hours today from 2:30 to 4 p.m. Can I have a show of hands of who's planning on coming to office hours with me today? I don't know yet. Okay, but I'm seeing around 4 or 5, maybe 6 people, so we'll plan on being in my office unless a lot of people end up showing up, and then we'll move down to a classroom, and I'll send an email through the system, and I'll put a note on my door. Okay? All right, so that's what we're going to do for office hours today. If you can't make it to office hours, but you still want to study for the quiz, go to the tutoring center. You can bring your homeworks, and you can show them your homework 1.6, 1.7, 1.8, there is no 1.9 homework, but you can show them your 2.1 and 2.2 homework, and then you can say, what do you think I should study for this quiz? What do you think is hard? And they can give you some problems to work on, they can help you practice, and so on and so forth. All right, so that's all I have to say, I think, administrative-wise. Any questions? Okay, then we're going to start for today by reminding you what we learned last time. So actually, I think last time we had to finish 1.9, so let me go back to 1.9. Oh yes, we were doing inverse functions. Okay, so we learned how to check we learned how to check whether First, we learned how to find the inverse if we have a formula. If we have a function rule, the way we find the inverse is by doing what? What should I do if I want to find the inverse of a function like this? I plug in y for x, and I plug in x for y, and then what? Then solve for y, right? Then get y by itself. And that'll be the inverse function. And the cool thing about the inverse function is it undoes whatever our function does. If our function turns 1 into 5, then our inverse function turns 5 into 1. Okay? And that was the properties of the inverse function. Okay, so f inverse of f of x is x, f of f inverse of x is x. And if there is a function g which satisfies these two properties, then it has to be the inverse. So that was how we checked. Okay, if we have a formula and we want to check whether these two functions are inverse or not, we could just try to plug in y here and put an x over here and solve for y. That would be fine. Or you can plug one into the other and the other into the one, and if you get x on both occasions, we're happy those two functions are inverses. The last thing that I said was, of course, the graph of an inverse is going to be the graph of the original function reflected about the line y equals x. Reflected about the line y equals x. So that was about the function graph. Any questions on inverses? Okay, it doesn't seem like there are. So let's go to chapter 2, where we learned about quadratic functions. And the first thing we learned about quadratic functions was the difference between general form and standard form. So standard form, or vertex form as I like to call it, is the form where you can see where the vertex is. The vertex is going to be at hk, right? So all we have to do to graph something like this is find the point hk and then adjust by whatever the stretch factor is and draw a parabola. Okay, so that was vertex form. So we practiced sketching, and then we practiced converting to vertex form from general form. The way that that was done was by this process here. So let me re-explain it. First, we factor an a out of the first two terms, and then all we do is we do the process of completing the square for this guy inside. So to complete the square, what I'm supposed to do is take this number, divide by 2, and square it. So if I divide that number by 2, I get b over 2a. You can see that here. And if I square that, then I get b squared over 4a squared. So if I take that number, divide it by 2 and square it, I add and subtract, then this whole thing here can get turned into a perfect square, like shown. And then the remaining minus b squared over 4a squared gets multiplied by a and summed with c. Okay, so this guy just basically comes out of the parentheses. Of course, if we bring it out, we have to do that multiplication by a. And that's how we get it into vertex form. So we saw a practice here. We didn't actually try this with a partner, but let me go through it one more time. In fact, let me just start over altogether. So I have 2x squared plus 8x minus 10. The first step says I need to bring a 2 out of the first two terms. Not 8, but 4x. By the way, if you can't pull a 2 out of that number, it's fine. Just write it as an improper fraction, okay? Then what am I going to do? I'm going to complete the square inside. How do I complete the square for x squared plus 4x? Someone help me out. Okay, 4 is not very descriptive. What do I need to do with 4? I need to take this number 4, and then I need to do what to it? I do need to square it, but before I square it, I need to do something else. Divide by 2. Okay, divide by 2 and square. Sorry, it's a little hard for me to hear sometimes up here, so sometimes I miss what you're saying. Okay, I need to divide by 2 and square. So, after I get that number, what do I do? So 4 divided by 2, all squared, that's 4, right? Because 4 divided by 2 is 2, square 2, I get 4. So I got the number. What do I do with it? You add and subtract it. Thank you for helping me with that. X squared plus 4x, and then I add 4, and then I minus 4. And the whole point was I wanted to create this. I wanted to create this, but I only had this, so I had to buy a 4. I had to buy a 4, and if I buy a 4, I have to pay with a 4, okay? So I bought a 4, and I paid $4 for it, and now I just need to simplify this. So this can be factored as x plus 2 and x plus 2, right? So what am I going to put in my parentheses? It's going to be x plus 2 all squared. Now, I still have to deal with this pesky minus 4 here. So it's going to actually come out of the parentheses as a minus what? 8, right? Because I have to do the multiplication of 2 times negative 4. And then I still have the minus 10. So now I get 2. So these are equal, equal, equal. I have 2x plus 2 all squared minus 18. So where is the vertex of this parabola? Negative 2. And then negative 18, right? Good. Okay, negative 2, negative 18. So it's kind of weird because this one, we got to change the sign, right? But the one that's outside, you can think of it as being like a vertical shift, right? Down 18 units, okay? And then you can think of this inside as being a horizontal shift to the left 2 units, right? Okay, I should not say left and then right. in quick succession like that. To the left 2 units is what that is going to produce. Okay, so let's draw it. So here is the point where the vertex is going to be. It should be at -2, -18. That's somewhere down here, right? And is it going to open up or down? Up. Why up? Because what is positive? The coefficient on x squared is a positive number, namely 2. Okay, so, and it's also going to be stretched by a factor of 2, right? So if I go over 1, how much am I going to go up? I'm going to go up 2 instead of the usual 1. So maybe I'll just do it like that. And then if I go over 2, how much am I going to go up instead of the usual 4? I would go up 8, right? So this would be the point 0, comma, -10. This would be the point -1, comma, what do we go up 2 again? Is that right? So -1, comma, -16. Okay, and then on the other side, what would I have? I'd have -3, comma, -16, and I would have -4, comma, -10, right? So it looks something like that. Okay, obviously this is not drawn to scale, but we have the points on here and we have the general shape. Okay, so that's how we convert to vertex form. And then once we have it in vertex form, it's relatively easier to graph. And I don't say that it's easy, I just say that it's easier than trying to graph something like this. All right, so that finishes up what we did last time. Any questions on quadratic functions so far? Yeah, Connor.
When you like divide by 2 and squared,
yep.
Where does that number go? Is that like what you're adding and subtracting?
Exactly. So my goal is, I have a function, right? If I add 4, then I changed it, right? But if I add 0 to something, I haven't changed anything at all, right? If I add and subtract 4 at the same time, it's kind of like adding 0, right?
So when you're looking for like the C term, you always just divide the middle by 2 and square it.
Exactly, yeah. So that's called completing the square. The way we do it is we take whatever this number is, okay, whatever's attached to the x, right? Whatever's attached to x. We take that number, we divide it by 2 and square it. That's the number, that is the number that we need to add and subtract. Because if we add it, then we create a quadratic function, which, when we factor it, will give us 2 of the same factor, right? When we factored this, we got x plus 2 and x plus 2, right? So it's by design, we chose to add and subtract the number 4 specifically in order to establish this double root for this quadratic so that we could factor it as a square term. Because when we have a square term like this and we add something at the end and multiply by something, then it's in vertex form and we can see how to graph it. Does that answer your question? All right, Chris. How do I get from -16 to -10? Okay, so this again comes from last time. So let's remember what our original parabola looks like, right? It starts at 0, 0. If I go over 1, what's the new point? 1, comma. Well, if I take y equals x squared, then I plug just the x value into x squared, right? So if I'm plugging in 1, what do I get? 1, right? And if I go over 2 units, then this point will be the point 2, comma, 4, right? I get 4 because I plug it into x squared, yeah? So what I need to remember is that this is a transformation of this graph, okay? Except it has a vertical stretch by 2, right? So if I were to stretch this thing by 2, then the height of each point would get multiplied by 2. So instead of 1, comma 1, I would have 1, comma 2. And instead of 2, comma 4, I would have 2, comma 8. Yes? So all I'm doing now is I'm taking this stretched parabola and I'm going to move it down here. Yeah? Does that make sense? So when I said, well, I'm going to go over 1, how much do I need to go up? I'm just remembering that on the normal graph of x squared, I need to go up 1. But since this is a stretch by a factor of 2, if I go over 1 on my transformation, I need to go up not 1, but 2. And then since I would normally go up 4, okay, I would normally go up 4 if I were going over 2. Then if I go over 2, I need to go up by twice that amount. And go up by 8. So negative 18 plus 8 gave me negative 10. Does that answer your question? Cool. Any other questions on what we've done so far today? All right, then let's talk about something new. Okay, let's talk about the range of quadratic functions. Okay, well, let's think about this rationally, or irrationally, whatever your choice. Okay, so we have a quadratic function, f of x, and it's in vertex form, which means the vertex is going to be at what, comma, what? If I have x minus h and then plus k, is the vertex going to be at minus hk? No, just hk, okay? So don't forget, there's a minus here, but there's a plus here. That's because minus on the inside makes us go to the right. Plus on the outside makes us go up, right? Okay, so, and let me fix that, because that's just not right. That's better. Or is it? Yeah, that is better. Okay, so hk. So here's the point, h comma k, maybe. Or it could be anywhere else. But the point is, if a is positive, which direction is the quadratic going to open? It's going to open up. Yes? If I have a quadratic function which opens up, then how can we describe the range? The range is the set of all possible y values, right? So the smallest y value is this one, right? And then we have all the other y values which go up from there, yes? So what is the range going to be for my quadratic function which opens up? K to infinity, good. And I'm going to include k, because k is actually achieved at the vertex, right? Okay, so that was not too hard. What about if it opens down? Well, if it opens down, then I have the point h comma k, and my parabola opens like this. What is the range of this kind of a function going to be? Good, negative infinity up to k, right? Should I include k? Yes, I should, because it's at the vertex, right? Okay, so that's pretty simple. I think finding the range of a quadratic function is really, really easy as long as you have it in vertex form. Because basically you know, well, it opens up and it starts at k, so we go from k up from there, right? Or it starts at k and it goes down, so not too tricky, I hope, to find the range of a quadratic function. Any questions on that? Okay, then let's talk about the discriminant. Okay, who's heard of the discriminant before? Okay, only a handful of us, so let's talk about it. So the discriminant, by the way, I have no idea why they call it that. Discriminant. I don't know. Anyways, it helps us tell basically when a function is, when a quadratic function is going to have real roots or double roots or complex roots, basically. But we're not going to worry about complex roots. Okay. What we're going to worry about is how many real roots does the quadratic function have? So you're going to notice that the discriminant is defined by b squared minus 4ac. Does that remind you of anything?
What's inside of the quadratic formula?
It's what's inside of the square root on the quadratic formula, right? We have x equals negative b plus or minus the square root of b squared minus 4ac, right? All over 2a. So the discriminant is just what's under the square root, right? So what kind of numbers am I going to get from doing this plus or minus operation if d is a positive number? Well, if d is a positive number, okay, if I take the square root of a positive number, I get something which is positive if this is the principal square root, right? So I have a plus or minus, meaning I either add something or I subtract something. But what we need to know is that that thing is not 0, right? So if I add or subtract something, I'm going to get f of x has 2 real roots. And what about if d is equal to 0? Well, if d is equal to 0, then I take the square root of it. And what's the square root of 0? Just 0. So if I take negative b and I add 0, or I subtract 0, am I going to get two different numbers? No, I'm just going to get the one number, right? Because adding 0 and subtracting 0 is the same thing. So I'm going to get f of x has how many real roots, do we think? Probably one real root, right? Okay, and how about if d is less than 0? Well, if I'm doing the square root of a negative number, what's the problem? You can't. The problem is you can't. So I can't take the square root of a negative number. Well, you can, but not in this class, I guess. So it would be a complex number, right? So when I say there would be 0 real roots, okay, f of x has no real roots. It does have 2 complex roots, if you care to know. All right, so this is basically what the discriminant tells us about our function. So what does it look like if our function has 2 real roots? If our function has 2 real roots, it's going to pass underneath the x-axis and then back up. Or if it opens down, then it's basically going to have 2 X-intercepts, right? 2 X-intercepts. What does it look like if we just have 1 real root? It means the vertex is on the x-axis. I love that precision of mathematical language there. That's a very good way of saying that. The vertex is going to be on the x-axis, okay? It could look like this, or maybe it could look like this or something like that, okay? That's the idea. And if we have no real roots, then what is it going to look like? Well, it's not going to have any x-intercepts. What does a parabola look like if it doesn't have any x-intercepts? Yeah, it's just floating. Okay, up here maybe. Or it could also be down here. Yes? Okay, it just doesn't touch the x-axis. Okay, that's also a possibility. All right, so this is what the discriminant tells us about our quadratic function. Okay, so let's see some examples regarding that. Okay, how many x-intercepts does f of x equals this guy have? Well, I know I just need to get the discriminant and check if it's positive, 0, or negative. So I know that the discriminant is b squared minus 4ac, which is just, well, b is 12, right? So what's b squared? 144. And I'm going to subtract from that 4 times ac. Now c is negative 7 and a is 3, so I'm going to subtract 4 times 3 times negative 7, which means I'm going to get 144 plus, right, I'm going to change that to a plus since I have 2 negatives here. And what am I going to get? I'm going to get 21 times 4 is 84, right? Okay, so I think that would be 228. Yeah? 228. Okay, so what can we conclude? Therefore, D is what? Positive, right? What did it mean when D was positive? There's 2 real roots. Good. To check that, all you have to do is go back to your notes and check. Aha, if D is bigger than 0, f of x has 2 real roots. Done. Submit. Okay, that's all I want to say about quadratic functions. For the time being, anyway. Are there any questions?
Are you going to ask us to find X-Intercepts?
Well, asking you to find the X-Intercepts should be very familiar to you, because if I want to find the X-Intercepts, what am I trying to do? I'm trying to find the values x such that if I plug them into ax squared plus bx plus c, I get what as an output? 0. So if I'm trying to do that, then what would I do? I'd use factoring or the quadratic formula. So yeah, that'd be fair game for sure.
I should know if it would be multiple points, like how many X-Intercepts and
Well, right. So, I mean, loosely speaking, everything we talk about in class is fair game for the homework. But if you don't see any questions like that on the homework, then you know they're not going to show up on the exam, right? So just make sure that you keep track in your mind of what sorts of things have been asked on the homework, because the exam questions and the quiz questions come directly from the homework assignments. I just copy them word for word. Well, I change the numbers so that they work out without a calculator. But yeah, I pretty much just copy them. Okay, so that's how you can tell what sorts of things I'll ask for on a quiz or exam. All right, then we're going to switch gears and talk about polynomials. Yeah.
We have a homework due tonight, right?
Yeah.
Is that the only homework that we have?
I talked about that at the start of class. We have 1.8 due today, 2.1 and 2.2 will be due on Friday. Okay, so let's talk about polynomials. Which polynomials are really just a larger set of functions, right? A larger set of functions. So in particular, a quadratic function is a polynomial, but not necessarily the other way around, right? A polynomial could be like x cubed or x to the 5th or something like that, right? So what do polynomials look like? I write them in this general form, which I find people find really confusing before they get to understand these kinds of general forms. What does it mean? It's just to say we have a number times x to another number, okay? We have a number times x to another number, and basically one thing is true: an should not be 0. ai is a real number for I bigger than or equal to 1. And what else? N is a natural number. N is a natural number. Okay, so what does that mean? It needs to be a whole number, something like 3, okay? So no powers of 3.5, no powers of square roots, no powers of pi. It needs to be a number like 1, 2, 3, 4, 5, 6, 7, and so on. Okay, so we have, let's see some examples maybe. Example could be something like f of x equals 37.5 times x cubed plus x squared minus 17. Okay, so what do I need? I need the coefficients to just be real numbers. They just need to be real numbers, okay? But the powers, they need to be whole numbers, which are positive. Okay, they need to be positive whole numbers. Okay, and at the very end, I have 1 for the term which corresponds to x to the 0, right? But what is x to the 0? It's just 1. So that's why I don't write it there. Okay, so this is what a polynomial function looks like. So let's talk about the degree. Well, the degree is just the largest power of n. Okay? So for example, what degree is this polynomial? It's 3rd degree, right? Or 5th degree would be if we had an x to the 5th, or 9th degree would be if we had an x to the 9th, and so on and so forth. So we have special names for some of them. If the polynomial is a 2nd degree polynomial, we've already seen this, we call it a quadratic polynomial. And we actually have names for 3rd and 4th and 5th, and probably more than that, but those are the only ones that I know. Does anybody know what it is for the 3rd degree? That's right, cubic polynomial. Okay, so these are adjectives. Quadratic polynomial, cubic polynomial, right? All right, how about the 4th degree? This one's harder. That's right, it's quartic. Okay, and the 5th degree? Anyone know that one? Good, it's quintic. Does anybody know why quintic polynomials are extremely interesting as opposed to the other quadratic, cubic, and quartic polynomials? Nobody's ever heard of this one, huh? Okay, well, you know how... That's okay. I wouldn't expect it. Okay, so you know for how quadratic polynomials, we have the quadratic formula, right? Negative b plus or minus the square root of b squared minus 4ac all over 2a, right? Well, a lesser known fact is there's also a formula to find the roots of a cubic polynomial, except it's insanely complicated. And there's also a formula like that for the quartic polynomial, which is also insanely complicated. Like, you could never possibly memorize it. But it does exist, and you could plug in the coefficients and just get the roots of that polynomial. But famously, extremely famously, like one of the most famous problems in all of mathematics was people were looking for a similar formula for the 5th degree polynomial for like hundreds of years, until a teenager proved that it actually can't be done. And that teenager's name was, I don't even remember his first name, but his last name was Galois. He was a French mathematician who basically grew up at around the time of the French Revolution. And he has a really fascinating story, which I'll regale you with just briefly. He basically was a terrorist in the French Revolution. He was involved in the revolution, and he basically got sent to jail. And while he was in jail, he proved that the 5th degree polynomial is not solvable by radicals, which is what it means to be able to have a formula like this. But the really interesting thing is he sent this information off to like some universities where there were people who had been working on this problem forever, and everyone was like, this is poppycock. There's no way a 17-year-old actually solved this problem. But he had, and he basically got turned down by every university. They said, no, we're not interested in having you. This is totally ridiculous, blah, blah, blah. Anyways, he gets out of prison, and it turns out that while he was in prison, his girlfriend started a relationship with another man. And so what do you do when your girlfriend starts a relationship with another man in 18th century France? You challenge them to a duel. So that's exactly what Galois did. He challenged this man to a duel, and he died in a pistol fight.
Wow.
So this guy had a really interesting story, and mathematicians today say that mathematics was set back by centuries with his death because he was that visionary. Anyways, fun story about the quintic polynomial. All right. Well, I hope you enjoyed that as much as I did the first time I heard it, because I thought that's just insane. But let's talk about polynomials. So we've got the quadratic, the cubic, the quartic, and the famous quintic. Let's talk about the graphs of these types of functions. Well, if we have a polynomial function, one interesting thing, sorry, just checking how much time I have. One interesting thing about the graphs of polynomials is that they are always smooth and continuous, okay? So they'll look something like this, maybe, okay? This is what the graph of a polynomial looks like. When I say smooth, what do I mean? I mean there are no corners, okay? So no absolute value type kinks, okay? No corners, no kinks. That's what I mean by smooth. Can anyone tell me what I mean by continuous? Sorry, can someone say that again? Sorry? It goes on forever. That's one way of thinking about it. Another way of thinking about it is that I can draw it without picking up my pencil. Okay, I can draw it without picking up my pencil. So here's an example of a continuous function. A not continuous function could look something like this. Okay, I can't draw something like that without picking up my pencil, can I? Okay, so this is not continuous, and let me also add a part of this where there's like a kink or something like that. Okay, so this is not smooth because there's a kink, and it's not continuous because there's a jump. Okay, so polynomial functions are nice and smooth. They're like rolling hills, okay? Like rolling hills. All right. And the domain of a polynomial is always all real numbers. Why does that make sense? Well, if I look at a polynomial, what do I have to do? All I have to do is take those numbers to various powers and then multiply them by another number. So there's no problem. There's no like division by 0. There's no square roots. There's nothing I need to worry about in the domain. So the domain of a polynomial function is always all real numbers. All right, so that's about the graph in the domain. Let's talk about a specific type of polynomial function, and that's the power function. We've already talked about this several times before. Actually, technically speaking, a power function is not a... Okay. Technically speaking, a power function is not a polynomial. It is a polynomial if n is a natural number. Okay? It is a polynomial if the power n here is a natural number, because then this would be something like 3x squared. Okay, that kind of power function is a polynomial. The type of power function that is a polynomial is something like this. Is a polynomial and a power function. But something like 3x to the 1/3 is a power function, but not a polynomial. Okay? All right, so we have ax to the n. A needs to not be 0, and n needs to not be 0, and they need to both be real numbers. Okay? If it's also true, in addition to that, that n is a natural number, then we can also call it a polynomial. All right, so that's power functions. Let's talk about even degree and odd degree. Okay, so what does even degree and odd degree mean in the context of polynomials? Well, if I have f of x equals an x to the n plus dot 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 plus a1 x plus a0, then this term here is what we call the leading term. And it tells us the degree is n. Okay, it tells us the degree is n. It's the highest power of x that we have. And if n is even, then we have even degree. And I'll leave it to you to figure out what it means when I say that it has odd degree. I think you can figure it out from there. Okay. Any questions so far on what did we cover recently? Okay, we did the graphs, domain of polynomial functions. We did power functions, and when a polynomial has even or odd degree. Okay, then let's move on and talk about end behavior. Okay, end behavior, okay, is basically, okay, I'm going to introduce some new notation during this part, so I'll go slow. So end behavior is what happens to the function, to the height of the function, when x does something which we call approaches infinity, okay, or approaches negative infinity. Okay, or approaches negative infinity. And the notation we use for that is we draw an x, and then we do an arrow, and then we do an infinity symbol. And that means that we're going to allow x to become larger and larger and larger and larger. Okay, and we want to know what happens to the function value, the height of the function, when x gets really, really big. Okay? So the way we write that is using the following notation. I write lim. Okay, I write lim. Does anybody... Oh, okay, never mind. I was going to ask, does anybody know what lim stands for, but it's written right here, right? Lim stands for limit, okay? So we say the limit of f of x as x approaches infinity. And this is what we are going to use to describe what is the height of the function becoming when x becomes incredibly large. And here is an example of what we say when we want to talk about the limit of f of x as x approaches negative infinity. We just replace the infinity symbol here by a negative infinity. And that's how we say x is going to become negative infinity. Okay, so let's see some examples really quickly of that. So let's take the function f of x equals x squared. Well, we know what the graph of f of x equals x squared is. It's a parabola, right? Okay, so the question is, as x goes to infinity, so the x value is marching way to the right. What is happening to the height of the function as the x value is marching really, really far to the right? The y value is becoming really, really big, yes? Okay, it becomes bigger and bigger and bigger and bigger and bigger the further and further we go to the right. Is that clear from the graph? Okay, it also makes sense since if I plug in a bigger number for x, I'm going to get a bigger number as the output of x squared, right? So in this case, we would say that the limit as x goes to infinity of f of x is going to be what? Well, as x goes to infinity, x squared is even bigger than that, right? So it's also going to infinity. Okay? Can anybody describe for me why I don't write infinity squared? Why don't I put a squared here? Yeah, because infinity isn't a number. It's a concept, right? It's just a symbol we use to describe the fact that this function is growing without bound. Okay? So it's not about the end destination. It's about the journey, kind of. It's about, okay, I'm going to go infinitely far in that direction. I'm never going to make it infinitely far in that direction, but it's perfectly fine for me to say I'm going to go infinitely far in that direction, meaning I'm just never going to stop going that way, right? That makes sense. Saying that I've gone infinitely far doesn't make sense, right? Okay, so that's why I don't write infinity squared. So as x goes to infinity, f of x goes to infinity as well. It's just a bigger infinity. It goes to infinity faster, but it's still going to infinity. All right. So how about if x goes to negative infinity? So I'm going to let x march along the x-axis, and I'm going to check what is happening to the height of the function as x becomes really negative. What is happening to the height of the function?
You're still going towards infinity.
Still going to infinity, because whether I go to the right or to the left, the function, it goes up, right? Okay, so that's how I do establish the end behavior of a function like f of x equals x squared. Okay, any questions on this limit process? For now, I'm not saying anything about the actual algebraic method of computing this. I'm just saying, well, let's look at the graph. Let's ask ourselves what happens when x becomes really large, right? You could also algebraically say, well, if x becomes really large, right, what is happening to x squared, right? Well, x squared is going to be something like infinity squared, right, which would just be infinity, okay? That's maybe one heuristic way that you could look at it, algebraically speaking. But what we really want to think about is basically what types of numbers do I get when I plug in an x value that is unbelievably large? Okay, that's basically what I want to think of. Or unbelievably negative and large. Okay, so that's limit. And let's see another example of a limit. Okay, this one's a lot more complicated. I've got a negative 523 x to the 7th power. Okay, well, let's imagine, okay, what is going to happen if x is an extremely large number? If x is extremely large and positive. Am I out of time?
No.
Okay. If x is extremely large and positive, then negative 523x to the 7th will be, and I want to describe what this number will be. Well, if x is extremely large and positive, then if I take that number to the 7th power, is it going to change sign? No, it's not going to change sign if I take it to the 7th power, but it is going to get a whole lot bigger, right? So it's even bigger, and then I take that number, that extremely big and positive number, and I multiply it by negative 523. What does that give me? A really big negative number. Okay, and if I plug in an even bigger number, then x to the 7th will be even larger, and therefore negative 523 times x to the 7 will be even larger and still negative, right? So what would we say about the limit as x goes to infinity of this function? Negative infinity, right? Because when x becomes unbelievably large, the function value becomes unbelievably large and negative. Okay, now let's ask ourselves what happens if we go in the opposite direction. If x is an extremely large negative number, and I take it to the 7th power, what's going to happen? It's still going to be negative, right? Because it's an odd power of a negative number. And then I take that big negative number, and I multiply it by negative 523. What does that give me?
Positive.
A big positive number. So what is going to be the limit as x goes to negative infinity of f of x? It's going to be positive infinity in this case, okay? So if you want to know, you can use this to inform the graph of your function. And it's also a fact that we go to 9:45 today, right? Okay. It's also a fact that if I have just an odd-powered power function, it's going to look something like x cubed, right? X cubed looks like this. But of course, it's negative, so it's actually going to be flipped. It's going to look something like this, maybe. Oops, that's not very good. It's going to look something like this. Okay, so this is what you can think of, right? So as x becomes really, really big, we already checked, the function value becomes really, really big and negative, meaning that the height is going down, 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 down. Okay, if we go to the left, as x becomes really, really large and negative, we're going to the left, 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 left. What's happening to the function? It's going up, 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 up. Okay. Any questions on these two examples of finding out the end behavior? Okay, so one thing I'll just mention in passing is that the end behavior of an even-powered function is going to be the same on both sides. Why should we expect that to be true? Why should the end behavior of an even-powered function be the same on both sides? Because if you take a negative number and you square it, you get the same thing as if you took the positive version of that number and square it, right? Or any even power, right? Even powers cancel out those negatives, right? But if we have an odd power function, okay, we're going to have opposite behavior on one side as we do to the other side, okay? All right, so even power could look like this, or it could look like, you know, this or something like that, but the ends go in the same direction, right? Or they could also go in the same direction going down if it was like negative x squared, right? Okay, so that's end behavior. Let's talk some more about end behavior, which is going to be the leading term test. Okay, so what does the leading term test say? The leading term test says that if you want to know what is the end behavior, of a polynomial with lots of terms, it turns out the only one that matters is the leading term with the highest power of x. Okay, so why should that be true? Well, it should be true because when we're talking about end behavior, we're talking about plugging in like really massive, huge values for x, okay? And if I take a really big number and I take it to the nth power, as opposed to, say, the n minus 1th power, when I plug it into the larger power, it's going to be like much, much bigger. Okay, let's take, for example, let me draw another page here, just to illustrate this example. Let's look at x versus x squared versus x cubed. And let's try plugging in x equals 1 billion. Well, if I plug it into x, I get 1 bill, right? What do I get if I plug it into x squared? I get 1 billion squared versus 1 billion cubed. Okay, so what's interesting about these numbers? Well, what you notice is when x is really small, like 1, okay, then 1 versus 1 squared versus 1 cubed, they're all the same. 2 versus 2 squared versus 2 cubed, they're not that far apart. It's like 2, 4, and 8. But 1 billion versus 1 billion squared versus 1 billion cubed, this one is 1 billion times as large as the first one. And this one is 1 billion times as large as the other thing, right? So the difference here is that these ones are basically negligible compared to something that is 1 billion times as large as it, right? If someone has 1 billion times as much money as I do, then they're like a Jeff Bezos, right? And they're like a, I don't even like remotely compare, right? Okay. So that's the point of why the leading term test is good for determining end behavior. So what does it mean? It means the only thing we have to look for is the largest power of x when we're trying to find end behavior. So let's see an example. Well, what's the largest power of x in this function? It's x to the 7th, and the corresponding term is minus x to the 7th. Okay, so this is going to determine end behavior. Why? Because when x is extremely big, this is going to be the largest term by a long shot. Okay? And these two terms are going to be so small that you can basically ignore them. Okay, so this is the one that determines end behavior. So, x goes to positive infinity. I take it to the 7th power. It's still really, really big. But then I make it negative. Now it's really, really big and negative. So this one's going to be negative infinity. Let's try negative infinity. Well, if I take it to the 7th power, okay, if I take a really huge number to the 7th power, huge and negative number to the 7th power, it's going to still be extremely huge and negative. And then I make it negative again. Well, if I take a negative number and I make it negative, that means I make it positive, right? So that means I'm going to go to positive infinity. Okay, so that greatly simplifies finding out the end behavior, the limit as x goes to infinity and the limit as x goes to minus infinity of these functions is really quite easy, right? I don't need to pay attention to anything except for one little piece. And the one little piece is the piece which has the largest power of x. Yeah? Okay, any questions on finding end behavior for a polynomial with many terms? All right, then let's keep on trucking. And maybe, let's see how far we can make it. Maybe we can, no, we can't finish. But we'll do what we can. Okay, let's talk about the zeros. Okay, so the zeros of a polynomial. So TFAE is a mathematical abbreviation. What it means is the following are equivalent. Meaning that each of these goes both ways as an if and only if. Okay? Each of these statements goes each way as an if and only if. And also, since they each go both ways as an if and only if, you can take any two of them. And those are also an if and only if. Okay? So that is what the following are equivalent means. So, if 1 is true, then 3 is true, then 4 is true, 5 is true, and 2 is true. They're all true if one of them is true. So, let's see what are these statements. Well, the first statement says C is a 0 of f. Okay, that's more of a definitional statement. C is a 0 of f. What does that mean? It means that x equals C solves the equation f of x equals 0. So if I plug in C, I get 0. Okay? Namely, f of C is equal to 0, right? This is true. That is what it means for x equals C to be a solution of the equation f of x equals 0. So that is what it means when we say that C is a 0 of f. It means if we plug C into f, we get 0. Okay, another interpretation of that is that C is going to be an X-intercept of the function, okay? Right? The height of the function is 0. We just established that. So f of C equals 0. That means the height of the function is 0 when the x value is C. So that means that C is an X-intercept. Okay, likewise, what would the coordinates of that point be? The coordinates of that point would, of course, be C comma 0. which means that the point c comma 0 is on the graph of f of x. Okay, nothing groundbreaking here. But the last one is more interesting. It says x minus c is a factor of f of x. X minus c is a factor of f of x. Okay, why is that true? Say, take a polynomial like x squared plus 2x plus 1, right? Equals, you set it equal to 0, you solve for x, you get x plus 1 squared equals 0, therefore x equals negative 1 is a 0. Okay, the reason that x equals negative 1 is a 0 is because x plus 1 is a factor, right? If x plus 1 is a factor, then using the zero product property, we can determine that x equals minus 1 is a 0. So that is how we determine that x minus c would be a factor of f of x if c is a 0. And vice versa. If x minus c is a factor of f of x, we can determine that the value that x equals c solves the equation f of x equals 0. Right? Because then it would be 0 times something else, which is always 0. Okay. Any questions on this sequence of equivalent statements? I shouldn't say sequence, because this doesn't matter what the order is. I should say this collection of equivalent statements. All right, let's try an example. Okay, well, we're supposed to find the zeros of this function f of x equals x to the 4 minus 2x cubed minus 3x squared. So my goal is to say something about statement 1. Which statement do you think is going to help me to say something about number 1 for this function? So 1 of 2, 3, 4, or 5 is probably going to help us. Well, I guess, I mean, you could make an argument for any of them helping you, couldn't you? Yeah, 2 could help, but mainly the one I'm looking at for the most part is, well, I want to find the zeros, right? Which means I want to set this equal to 0. So you could think of that as being statement number 2, right? But then how would I solve an equation like this? You'd use number 5, right? You'd factor and use the zero product property. Okay, so let's go ahead and do that. So I'm going to solve using 5. Okay, so x to the 4 minus 2x cubed minus 3x squared equals to 0. I want to factor the left-hand side. What is the number one thing that I should do when I'm factoring? The very first step, if I can do it, is to do what? Greatest common factor. What is the greatest common factor between x to the 4th, x cubed, and x squared? It's x squared. So if I take an x squared out, I'm left with x squared minus 2x minus 3 equals to 0. Okay. It's extremely important that we take that x squared out, right? Why is it extremely important? Because how else are you going to factor this? This is a quartic, right? We never learned how to factor quartics, did we? We learned how to factor quadratics and how to take GCFs out. So if you see a quartic and it says factor, unless it's quadratic by form or something like that, then you need to take a GCF out. So that's how we take the GCF out. And now I can be left to just factor the inside here, which how is that going to factor? I need two numbers, which if I add them together, I get negative 2, and if I multiply them together, I get negative 3. It's negative 3 and positive 1. Good. Right? Because negative 3 plus 1 would give me negative 2. But if I did negative 3 times 1, I would get negative 3. Okay, so we successfully factored. And now what? Now what must I apply to solve this equation? Or am I done? Right, I need to find the zeros. But in order to do that, I need to make a logical claim, right? And the logical claim says if I have one thing times another thing times another thing, and I got 0, then what must be true about one of those things? One of those things has to be 0. Does anybody remember the name for that line of reasoning? Good. Zero product property. Okay, so it says the zero product property tells us, or it implies that then either x squared is 0, or x minus 3 is 0, or x plus 1 is 0. This is what the zero product property says. It says if I take 3 things and multiply together and I get 0, then one of them, at least one of them, had to be 0. Okay, so if x squared is equal to 0, then x is equal to 0. If x minus 3 is equal to 0, then x equals 3. If x plus 1 is equal to 0, then x equals negative 1. And those are my zeros. Okay, so this is actually review, I think, from when we studied polynomial equations back in the appendix chapter. But maybe we have a little bit more robust understanding of it now that we have a better context for polynomials, right? Okay, so this is how we find the zeros. Any questions on how we did this one? We took the GCF and then we factored and we used the zero product property. All right, no questions, so we move on to the last thing we're going to talk about today, which is the intermediate value theorem. And the intermediate value theorem, which is given in the book, is complete BS. So we're not going to use that intermediate value theorem because I don't know what they were thinking. It seems like what they wanted to do is basically dumb it down a little bit. But I feel like they just made it more confusing than it already is. So we're going to give it in the more general form. Which the intermediate value theorem, which is given in the book, is more specific for an unknown reason. And it doesn't really make it easier. So, okay, anyways, let's see what the theorem says. The theorem says one number is smaller than another number if f is a continuous function, which, by the way, did we learn any specific types of continuous functions today in class? Yeah, polynomials are definitely continuous functions, right? Then, for each value c, which lies between the outputs of f of a and f of b, there exists an input in between a and b such that the height of the function at that input is that chosen height. Okay, it's really hard to see when you see the definition written out like this, so let me draw the picture. So, we have a continuous function. Nice and smooth, and I can draw it without picking up my pencil. And I have one number a, and I have another number b. Okay? And this is the point a comma f of a. Yes? No, sorry. This is the point b comma f of b. B comma f of b. And this is the point a comma f of a. Okay, this is the point A comma f of A. Then what does it say? It says that for each value C which lies in between f of A and f of B. Okay, so here's f of A. And here is f of B. So for every choice of C which is between those two, for every choice of C which is between the heights of the two endpoints, for every height which is between the height of the first point and the height of the second point, then there is an input somewhere in the middle, such that the height of the function at that point is equal to that height. So here is xc, the input, which produces this chosen height. So loosely speaking, what does this mean? What I want you all to imagine is just forget about all this math for a second and imagine the following. If I am flying on an airplane and I'm flying at 10,000 feet at 2 p.m., I'm flying at 10,000 feet. And then at 3 p.m. later, I'm flying at 30,000 feet, much higher than I was before. Then at some time in between 2 and 3, I was flying at 20,000 feet, or 25,000 feet, or any height in between 10,000 and 30,000, right? If I just go up, on the airplane or something like this, then I have to touch every height in between my starting height and my ending height, right? Or if I'm going down, if I start on the 10th floor of this building and I get in the elevator and I go to the first floor, then at some point, while I was on the elevator, I was on the 9th floor, the 8th floor, the 7th floor, and so on and so forth. That's all that this theorem says. Okay, so we'll stop there for today. Thanks for your attention, and don't forget I have office hours in my office later today.